Hi and welcome to this flipped learning video on fossil fuels. This is topic C2 in the IB Chemistry SL. So let's start by, as always, having a look at the study guide. So as we have a limited amount of time, I'm mostly going to focus on the parts of the study design that aren't general knowledge. So I'm going to talk about fractional distillation. I'm then going to talk about knocking an octane number, how that links to chain length and branching, and how reforming and cracking can change octane number. I'm then going to talk about, cracking and reforming. I'm going to talk about gasification and liquefaction and equations for those things. I'm going to, when I talk about fractional distillation, talk about uses, and I'm going to talk about carbon footprint and calculate. I'm also going to talk about advantages and disadvantages of some different fossil fuels. We did talk about that. Okay, so fractional distillation is, and I'm going to switch to my laser pointer. So basically what happens is you start with crude oil and you put it into a heated chamber. The heat source is down the bottom. Let me just note that. And I'm going to switch from a red pen because that entire diagram's red. So we have the heat source down the bottom. And basically what we end up doing is we end up heating up that crude oil until it evaporates. And as you move up the length of this, the temperature decreases. So up the very top, it is going to be coolest, and it's only those very, very small carbon chains that are gaseous at that point. So once we get to about 70, we're looking at the gasoline fraction. So C5 to C10 are what we use as fuel for cars. Once we're down here, our temperature's up at about 120. Naphtha, which used to be used as a chemical weapon in war, so pitch and naphtha, used to be used as, in old movies, not old movies, but movies where there's like catapults that are lobbing flaming balls of stuff. That's pitch and naphtha. So in this range here, we now use them for as chemical precursors. Kerosene used to be used in lamps, like household lamps. You used to fill them up with kero and light them. That's now mostly used for aircraft fuel. Diesel, which you can get from, sorry, I've lost the word, just from your local servo. They're used as fuel for cars and buses and lorries, like trucks. Fuel oil, which is even longer chain, so between C20 and C70. That's fuel for ships and power stations. And then there's a bunch of stuff that just is going to stay liquid pretty much no matter what. And that's bitumen for cars and roads. So the black tarry stuff that you put with the rocks to make like asphalt, that's bitumen. So basically, fractional distillation separates based on boiling point. Now, because these are all carbon chains, they are basically held together by LDF, which means that the longer the chain, it's going to have a higher boiling point. And one thing that we really should do before we even start this fractional distillation, for the acid deposition reasons that we spoke about in the acids and bases unit, you should try and get rid of sulfur. because otherwise you end up with a whole bunch of sulfur dioxides being in this mix. Now, once I've separated out, and I'm just going to switch back to my laser pointer, once I've separated out, say, the C5 to C10 fraction, I can then do another fractional distillation process with this fraction to try and narrow it down even more. So this separates them out into general fractions, but then I can then separate this out further using a more delicate version of this fractional distillation setup. So let's continue on. Now, this is where it's going to become very obvious that I am a chemistry teacher and not an engineer. Internal combustion engine. So you might have heard of a car being referred to as a 6-cylinder or a 4-cylinder. A cylinder is basically a piston. So you've got basically a piston, and as this piston moves up and down, it transfers this up and down kinetic energy into our engine. Now over here, and so in here, I would inject a mixture of fuel, so whether that's diesel or petrol, and oxygen from the air. So basically I inject in air, and this cylinder gets pushed down. The fuel and oxygen are injected, and then there is a little spark which combusts the fuel and oxygen and then explodes that piston back up. So piston goes down, fuel and oxygen are injected, it's sparked and it explodes up, and then it's that explosion upwards that drives the force of the engine. So in a 6-cylinder car, you have 6 of these things. In a 4-cylinder car, you have 4 of those things. So just let's think about it in terms of kinetics, because if in doubt, kinetics is always the topic you should think back to. So if I increase pressure, and because this gets hot, increase temperature, one of the things that can happen is that what if my piston doesn't quite make it all the way back down before my fuel explodes? You end up with like a hiccup where this piston doesn't quite fire properly and you get sort of an off-time explosion of the fuel because of the conditions that we basically create inside that internal combustion engine. Those off-time explosions of fuel and oxygen are what are called knocking. Now, this was a major problem for the early development of the internal combustion engine, and it basically stayed a problem until, and he's a fascinating character from scientific history because, like, he's basically on the list of people who have done the most harm to the environment without actually setting out to be harmful. There was a guy by the name of Thomas Midgley. I think I've spelt his surname correctly. He's well worth looking up because he came up with the idea of adding lead to petrol to stop knocking, and he came up with chlorofluorocarbons as a refrigerant. So he's quite an interesting character from the history of science. I do recommend looking him up. Let's talk a little bit more about knocking. Now, knocking is that auto ignition. So we don't want that fuel to auto-ignite. We want it to ignite only when we apply that spark so that we get that smooth transfer of energy through the cylinder. That is linked to octane number. So if something knocks, it means it has a low octane number. So the isooctane, which is a octane isomer, which is heavily branched, and heptane is just meth, eth, prop, but, pent, hex, hept. So heptane, you basically look at it the wrong way and it'll auto-ignite. Something like isooctane is heavily branched and it's much more resistant to that spontaneous combustion. Now, basically, octane number is so for any other petrol, I'm just going to actually call it a fuel. So for any other fuel, how does it ignite compared to a ratio of my isooctane and my heptane? Remembering that my heptane is easy to ignite and this is hard to ignite. Okay, let's continue on. So as you can see, this is the exact same picture I had earlier. There is a whole bunch of fractions here that are useful, but in limited amounts compared to these guys. So how can I take these guys and make them more useful? That's what we call cracking. So for example, if I had C10H22, so decane, I can actually break that down into octane. So 8 times 2 is 16, plus 2 is 18, plus, let's look at my decane. So I have 2 carbons left over, and I have 4 hydrogens left over. So this is ethane, which is super useful for plastics. Octane can be used and then modified using one of our next processes to be used for petrol. Not ethane, ethene, which is super useful for plastics. And then this octane can be modified to form petrol. So cracking hydrocarbons, the important thing to note is conservation of mass. So all of the carbons I started off with here have to end up in my product. All of the hydrogens have to end up in my product. I will always end up you know how I always tell you to do a does this make sense check? You will always end up with something that is unsaturated, which is good for our purposes a lot of the time because we do want to be making plastics. Okay, let's move on. So reforming is the process where we can take the slightly less useful straight chain hydrocarbons and convert them into forms that are more useful both for industry and to change their octane numbers for petrol. So in that first example, we can see, let me get my laser pointer out. Meth, eth, prop, but, pent, hex, hept. So this is heptane. And by converting it into a methyl benzene, and hydrogens. Methylbenzene is a really useful chemical derivative. Hydrogen can be used for a bunch of things, including the Haber process to make ammonia from nitrogen. I can also take meth, eth, prop-bute, hence, blah, 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 meth, eth, prop-bute, pent, hex, hept, oct. So this is octane, straight chain octane, which actually, as it turns out, has an octane number of, I think, -20. It explodes so readily. If I reform that into meth, eth, prop-bute, pent, hex, so 1,5-dimethyl-hexane, this has a much higher octane number, so it's much more resistant to knocking, so it's more useful in engines. So for reforming, again, we're looking at isomers. So you've got to make sure the number of carbons in reactants is equal to your number of carbons in products, and your number of hydrogens in reactants is the same as your hydrogens in your products. So you need to be able to form these reactions, much like cracking. It's about double checking that you've added up your carbons and hydrogens correctly. So reforming is basically switching between isomers. So it's either isomer formation or the forming of aromatics. So I described this structure in the organic topic as an aromatic. It's because in nature a lot of these things are smelly. So aromaticity has to do with the presence of these benzene type rings. Okay, let's continue on. So coal is reasonably widespread. It's becoming less widespread now that we've dug so much out of the ground. But gas and oil are more located. They're not as widely distributed. So what if you've got coal in your country, but you don't have gas and you don't have oil? So you can either coal gasification, which forms methane and things like that, or coal liquefaction, which forms our big, long carbon chains, that look like petrol, that look like oils. Okay, so let's continue on and talk about gasification and liquefaction. So coal gasification is the process where we can basically convert solid coal into a gaseous form that contains energy. So there are two main ways we can do this. We can either go indirect, or we can be a bit more direct about it now. So we can go carbon plus water makes carbon monoxide and hydrogen. I can then take my carbon monoxide and hydrogen, add a bit more hydrogen, 3H2, makes methane, CH4, and water. So this is a process where I'm heating it. It is that two-stage process. I need to pump in that extra hydrogen. Also, there's a more direct way where I can take two carbons and then heat them with water with a catalyst with a hydroxide catalyst, and I end up with methane, CH4, and CO2. Once I have my methane, Methane is a slightly less efficient source of energy than coal. So it's got a lower, like, kilojoules per mole, but it's much easier to transport. So one of the points that we'll come back to at the end of this presentation is the pros and cons of these various different types of fossil fuels. Gas has slightly lower kilojoules per mole, but it is a much easier way to transport. It's a much easier chemical to transport. So we can have a gas line going into our homes, but none of us really have like coal shuttles anymore for us to put coal like in our stoves. Okay, let's move on. Okay, so with coal liquefaction, our aim is to get effectively a crude oil. So coal liquefaction is particularly important for, to a lesser extent, countries like Australia, but South Africa is actually pretty well leading in this because they have really big coal reserves, but their oil reserves are comparatively low. So if there are like global fluctuations in oil prices, with enough coal liquefaction technologies, a country like South Africa might be able to insulate themselves from those price shocks on the world market. So basically, coal liquefaction starts from one of the methods that we saw in the previous slide. So we end up with carbon monoxide and hydrogen. So if we take, sorry, I'm just going to write my hydrogen the other side. So if I start with hydrogen and carbon monoxide, and I'm just going to say NCO, and 2N plus 1 hydrogens, we end up with CnH2n plus 2 plus N numbers of water. So hopefully you remember from organic chem, this is an alkane. And I would produce, so using this process, this is called the Fischer-Tropsch. And we need catalysts, so it's either iron or cobalt. I will need to double check the exam questions. I can't recall how much detail they actually expect you to know about this process. But once we've got our alkanes, that would be a mix of alkanes, so we would need to do fractional distillation on those. So I will find some exam questions for us on coal liquefaction and see what level of detail they expect you to know. I suspect it just says in the study guide deduction of equations. So if they tell you the number of moles of carbon monoxide that are being formed into our alkane, again, it basically comes down to balancing the equation. I will need to double check that though, so keep an eye out. Okay, let's continue on. Carbon footprint is a term that I am guessing you've heard before, but I'm just going to explain one or two like misconceptions about it. So we say carbon footprint, but it isn't just CO2. So the carbon footprint isn't just about carbon dioxide. The calculation takes in methane. It takes in nitrous oxides, sulfur oxides. So I'm just going to call those SOxes. takes in hydrofluorocarbons and a couple of other different types of gas. So basically, it isn't just a carbon footprint, it's a global warming impact footprint. But that isn't anywhere near as catchy, so we don't tend to call it that. Now, for me personally, and for most of us in Western societies, my transport, my taking my car to go down the shops, doesn't actually contribute as much to my carbon footprint as what I buy once I'm at the shops. So, for example, if I drive the 10 minutes to go to Aldi and then buy a steak, that steak has a higher carbon footprint than the 10 minutes of driving I did. So, one thing that we should be aware of in Western societies, I mean, in Australia in particular, and even more particularly in Victoria, the overwhelming majority of our electrical energy comes from coal-fired power stations. The overwhelming majority. Now, what that means is that me plugging in an electric device to charge it, as my laptop is now, that has a carbon footprint. I have a glass of milk. That milk has a carbon footprint. So, yes, the fact that I probably go overseas once a year, that has a big impact on my carbon footprint in terms of the choices I'm making. But in terms of energy supply, my choices that minimize carbon footprint are actually not that. There aren't that many options in Australia. Yes, there's carbon offsets, but that's basically planting a few trees and hoping for not a bushfire year. If my electricity were coming from nuclear or solar or tidal or hydro, yes, that would make a massive impact on my carbon footprint. But carbon footprint is a slightly larger umbrella than just the carbon dioxide that I personally create when I go out driving. It's also about the choices I make in my consumption. Okay, let's have a quick look at some of those choices I'm making. Okay, so hopefully this works. Now, because this is a reasonable length calculation, I did it earlier and I'm just going to click through and laser point my way through it. So, assuming my car uses pure octane isomers, what is the carbon footprint of a 200 kilometre drive? So I've grabbed this little Google snippet showing that the fuel consumption is 6.1 litres per 100k. So when I go to here, the volume of petrol I'm going to use is 12.2 litres because that's 2 times 6.1. Now, I am assuming that 1 litre is 1 dm3. That works for water. It's not quite the same for petrol, but I haven't given you that piece of information, so you can't actually do that calculation. So the mass of petrol is density times volume. I've told you the density. So it ends up being 748.9 grams per dm3, and I have 12.2 dm3 that I've used. So it ends up being 9,136.58 grams. So 9 kilos of petrol get used. So now I've got kilos of petrol. I now need to convert to moles of petrol. Now I've told you that it's pure octane isomers. So it's my mass divided by my molar mass, so C8H18, which gives you 5.231 mole. I then quickly ran through and balanced that equation. So you end up with C8H18 forms 8 CO2 and 9 H2O. So my number of moles of CO2 is going to equal 8 times my number of moles, and crap, sorry, I've just realised I put the wrong number in my calculator. So I actually accidentally put 5 in my calculator, so I need to go back. So if I go 8, that makes not 26.15 moles, but 41.85 mole, which ends up, when I multiply that by the molar mass of carbon dioxide, so CO2, I end up with not 1.2, but 1.8 kilograms. So that is the carbon footprint of me taking a 200k drive in my car. So this is a little screenshot from a recent energy bill of mine. You can see that for this bill, I released 0.11 tonnes of greenhouse gas emissions. Now, for my purposes, I am going to assume that this is equal to my mass of CO2. So my M of CO2 is 0.11 tonnes, which is equal to, so 1 tonne is 1,000 kilos, so it's going to be 110 kilograms, which is 110,000 grams. So my N of CO2, and I should give myself a bit more room, my N of CO2 is going to be mass divided by molar mass, which gives us, let me just get my calculator, 110,000 div 12.01 plus 32, because that's 2 16s, and that gives us 2499.4 mole. So, assuming that what I've burnt is pure coal, I have C solid plus oxygen gas forms CO2 gas, which means that my N of coal that I've burnt is that 2499.4 mole. Now, to convert that to mass of carbon, it's N times big M, which gives us that number that's already on my calculator times 12.01, which gives us, oh wow, that's quite a large number, 30018 grams, which is 30.0 kilograms. So I personally, over the course of, I think that was a month, I personally, my energy that I used was the equivalent of 30 kilos of coal. Cool. So let's just take a step back and talk about our different forms of fossil fuels and their pros and cons. Okay, so in terms of pros and cons, obviously these are all fossil fuels, so they've all got the con of increasing carbon dioxide in the atmosphere. I'm not going to write that in each of them. So natural gas, it burns pretty clean. So it's not going to make sulfur dioxides and things like that you find from coal. Remember, we talked about acid deposition, so it burns clean. It's really easily transported. And it's got a higher specific energy than oil or coal, so than those guys. So the cons is, yes, it contributes to global warming. There's a issue with distribution. It isn't a matter of everywhere in the world has access to it. It's not evenly spread. There's also fracking, which any mining term that was a swear word on Battlestar Galactica, we should probably take a second look at. And one thing that happened back when I was in high school, so 25 years ago now. Oh dear Lord, that's depressing. There was an explosion at a gas power station in Victoria, and like a fair proportion of Melburnians lost hot water and cooking. 2 people died in the explosion and it was awful. But there is the risk of explosion. So on that macro scale, if it happens at one of the power plants, or on the micro scale, if there's a gas leak in a house, that can also be super dangerous. Oil is also reasonably easy to transport. So you've probably been on the freeway and seen one of the big tankers driving past. Oils are also used as precursors for chemical industry. And this is the fuel for cars and trucks and planes. Now, as before, this does increase CO2. The other issue is that oil spills. So, of course, there's the Exxon Valdez if you want to go back a bit farther, but there was the Deepwater Horizon in the Gulf of Mexico, which is still being cleaned up. We are still seeing effects on wildlife, on fishing in the Gulf of Mexico because of the Deepwater Horizon spill. Now, coal is, so the distribution was a con looking at natural gas. Coal, it's actually reasonably evenly distributed. So the distribution of coal is comparatively well distributed. There's quite a lot of it. So So we can also do the chemical processes to convert into gas or oil. This has higher energy than renewables. It's also safer than nuclear, although I have some issues with that. I'd rather live next door to a nuclear power plant than a coal-fired power plant. One of the cons that these guys have, you might have heard of the term peak oil. One of the cons that these guys have is the actual amounts are limited. We could be running out of gas or oil within the next 50 years. The cons of coal, let's stick to coal for the moment. Because it's contaminated with sulfur, there's acid deposition. It's harder to transport, so transport is a con here. And it's actually dirty. So it's a dusty substance. So they've done studies around the trains that move the coal through, I think it's Queensland, And they've actually found that in those areas there's a higher rate of like PM90 particulates in the air that could be contributing to breathing issues in those areas. Coal mining is historically one of the most dangerous jobs, and it's responsible for quite a large number of deaths throughout history. Okay, let's move on. I've just realised how long this video is. Sorry about that, gents. Sorry about that to anybody who's watching it, but particularly to the 2 kids in class that I'm going to ask them to watch it as homework. So, overall, what we've talked about fractional distillation, that's petroleum and crude oil. We've talked about the various fractions of petroleum. We've then talked about knocking and octane number. We've talked about how branching affects the octane number. And we've talked about how we improve the octane number. We talked about fuels being improved by cracking and reforming. And we talked about equations for cracking and reforming. We talked about coal gasification and liquefaction, and we looked at the equations for those. We then talked about carbon footprint, and we calculated carbon footprint. We then discussed the advantages and disadvantages of the various fossil fuels, so oil, coal, and natural gas. Thank you so much. Have a lovely rest of your day, and I will see you next time. Bye.